be recorded, and all of these resources are going to be available for you after this preview today, and it will be uploaded to the teams. So I'm going to go ahead and share my screen, and we are going to get started. All right. So today we're going to do a Q3 science preview for you. And as always, we're going to start with some science announcements and updates for you. Our next virtual science CCC meeting date for 3rd through 5th grade science teachers is going to be March 16th. So go ahead and mark your calendars for that. I will be sending out a calendar request for that, or a meeting request, just to remind you, along with the Teams link where we will host that. The meeting will be recorded, of course, and posted to your grade level science team for later viewing, along with the PowerPoint and any resources that I do share during that presentation. Some CTLS updates. Unfortunately, there's a typo. It says K2, but 5th grade also now has science workshop model lesson plans for Q3 and 4 uploaded underneath the topic navigator tab. So you'll select a unit, whether it's physical or chemical changes or electricity, magnetism. Once you're there, you'll scroll down to see instructional strategies. And that's where you will find those science workshop model lessons. Also, our Title I science coach, Kelly Bodner, also created a virtual field trip document that's been uploaded to the course resources tab in your 5th grade science course on CTLS Teach. And then, of course, if you're having any cool science lessons, whether it's labs, investigations, maybe some presentations, or hosting a virtual science event, invite the science department to watch. We won't be able to join face-to-face just yet, but if you would send us the link, we will join you for your event. You can fill it out on this. We created a Microsoft form for you to do that. And it has already been uploaded to your teams probably about 6 weeks ago. So if you scroll up on Teams, you'll see that form as well. So here's what we're going to tackle today. We're going to go over the Q3 science standards. We're going to unpack those standards, and I'm going to give you some content knowledge to help you teach those standards. We're going to look at some lesson resources and plans that I have available for you based on those units. And then I'm here for any questions or feedback that you might have. And I'll show you some specific examples through my screen as well. So let's look at it. Here it is. This is your 5th grade science teaching and learning framework. It's located in CTLS Teach underneath the course and navigator tab. This is your landing page. This is what you will see when you open up your 5th grade science course. Q3 is kind of wonky because we have 3 units kind of smashed together that interconnects and interweaves throughout Q3, excuse me. So today, I know that a lot of you are probably finishing up cells and microorganisms, so I wanted to share with you something new. So we're going to be focusing on physical and chemical changes and electricity and magnetism for our preview today. So let's talk standards. Let's go ahead and unpack these standards and talk about some background knowledge that you might need to have in order to teach these standards effectively to your students. So I've unpacked these standards and highlighted in purple the 3 science and engineering practices that all of our science Georgia Standards of Excellence start with, and that is obtain, evaluate, and communicate information. And those are S&P practices, and students will be actively doing science with that. And then we have our standard elements that also are unpacked for you that have those science and engineering practices highlighted. And that's what students need to be able to do in order to master that standard. So for physical and chemical changes, we have obtain, evaluate, and communicate information to explain the differences between a physical change and a chemical change. Specifically, element A is plan and carry out investigations. So that means they need to do something. They're going to need to do an investigation by manipulating, separating, and mixing dry and liquid materials, and communicate collected data to demonstrate examples of physical change. So that element is all about physical change, separating, mixing, liquid, dry, and communicating those examples. Element B, constructing an argument based on observations. So they're going to do some science and observe what happens. And then they're going to develop an argument based on those observations. And an argument is a paragraph. It's writing. We're going to have to do some science writing. We can present it orally. We can do it in a paper form. You can pick different ways we can present it to an audience. As long as they're based on observations, that the physical changes in a state of water are due to temperature differences, which cause small particles that cannot be seen to move differently. So I have some examples of activities you can do to hit that element. And C, another doing science, plan and carry out an investigation. So we're going to be doing an experiment or a lab to determine if a chemical change occurred based on observable evidence. If there's color, gas, temperature change, odor, new substance provided, that's how we know that a chemical change has taken place. So with physical and chemical changes, there is some background knowledge that you need to know in order to do this effectively with your students. So for fifth graders, we need to try to keep it relatively simple, but students should know that there are alternative views as to what constitutes a change that is classified as chemical, physical, or both, right? So for the purpose of our standards, let's think of a physical change as a change that is reversible, okay? So the basic particles are not altered at all, although shape and size can be changed. So in a physical change, the matter remains the same. For example, water, ice, and steam are all what? H2O, right? Water. Physical changes include changes in phase, like the boiling of water, and changes in the shape and size of that material as well. So each of these changes in the condition of the material without changing the basic composition. So examples, molding shapes, clay, mud, hot steel, how you can mold them into a new shape, physical change. Whipping egg whites, you're adding air, but it's still egg whites. That's a physical change. Melting a cube opposed to burning a sugar cube, right? Cutting material, wood, plastic, paper, cloth, just a physical change. Butter melting, water boiling or freezing. Excuse me. Those are examples of physical changes. Now let's talk about chemical changes. A chemical change, on the other hand, does make a new substance, right? So the matter is different. The particles of that substance are broken down and the atoms or the molecules are rearranged, and that creates a new substance. So signs of a chemical change include changes in color, odor, temperature, and a change in state without adding energy. So an example of that would be a gas is produced when you add baking soda and vinegar together, okay? Other examples of a chemical change: milk going sour, jewelry tarnishing, rust forming on metals, the burning of a match. So think about hydrogen peroxide bubbles in a cut. That is a chemical change. Frying an egg, bread rising, vinegar and baking soda reacting, burning a sugar cube, really burning anything else like combustion, that's a chemical change. So while your students are investigating these changes, try to keep it simple, but also understand that difficult questions like the difference in melting and burning sugar, that might come up. And fortunately, students will explore these concepts in more detail when they take chemistry in high school, but it's, always best to be prepared and have some go-to plans and where you can kind of direct them to learn more or extend their thinking. So, excuse me, let's talk about states of different states and phases and matter of water, right? So fortunately for most of us are all familiar with gas, liquid, and solid states of water, right? And the fact that water changes between these states through heat, either the addition or reduction of heat energy. So since these changes don't alter the basic composition of water, it's still H2O, they are classified as a physical change. But we should anticipate that our students will also probably ask us about plasma. They probably heard about that fourth state of matter or fourth phase of matter. And while plasma isn't covered in the fifth grade standard, it's still interesting, right? So plasma is currently thought to be the most common state of matter in the universe. And it consists of like hot ionized gas particles. So on Earth, lightning can heat up the air enough to generate plasma, but it doesn't last very long at all. And then they might be familiar with plasma TVs, and they contain tiny amounts of plasma contained in very small cells. And these cells, when illuminated with ultraviolet light, they illuminate red, blue, and green phosphors, thus creating, the pixels or the colors on the screen. So obviously the process is way more complicated, but I suggest you let the students research this. And remember, plasma is not in the standard at all for our students. So let's talk about electricity and magnetism. So during this unit, your students are obtaining, evaluating, and communicating information to investigate electricity. So you have two standards for this. So for our electricity standards, the first element is obtain and combine information from multiple sources to explain the difference between naturally occurring electricity, static, and human harness electricity. So I'm going to give you some really cool station activities to do for that. B is design a complete, simple electric circuit and explain all necessary components. Have a really fun activity for that. And then C is plan and carry out investigations on common materials to determine if they are insulators or conductors of electricity. And then your second standard for this unit is obtain, evaluate, and communicate information about magnetism and its relationship to electricity. So element A, construct an argument based on experimental evidence to communicate the differences in function and purpose of an electromagnet and magnet. So look at how we've unpacked that standard. Construct an argument based on experimental evidence. So that means our students are going to have to be doing hands-on science with electromagnets and magnets. Okay. B, plan and carry out an investigation, more hands-on science, to observe the interaction between a magnetic field and a magnetic object. So let's talk about electricity a little bit. So we know electricity is a type of energy that can build up in one place, or like we think of it, flow from one place to another, right? So when electricity gathers in one place, it's known as static electricity, right? The word static means something doesn't move. We've all experienced this when we touch a door handle or a doorknob or rub a balloon on our hair, right? So electricity that moves from one place to another is called current electricity. So static electricity is produced when you rub two things together, right? If you rub a balloon against your shirt 20 or 30 times, you'll find the balloon sticks to you, and that's called static cling. We have that a lot. That's why we use dryer sheets with our clothes. And this happens because rubbing the balloon gives it an electric charge, which is just a small amount of electricity, and your shirt the opposite electrical charge, all right? And they attract to each other so that the balloon sticks to your shirt. So we talked about, current electricity is electricity that moves from one place to another, or a current. This is the type of electricity that we're most familiar with, and it's also the most useful for us humans, right? Current electricity involves the flow of negative particles, or what we call electrons, through conductors such as copper wires. We talked about a lightning bolt earlier, but a lightning bolt is also an example of an electric current, although it only lasts for a little while. So electrical currents provide power for all the electrical appliances that we use, like our stoves, refrigerators, televisions. So for an electric current to move, though, from one place to another, there must be a circuit. A circuit is a closed path or a loop around which an electric current flows. For example, a flashlight, right? There's a simple circuit with a switch, a lamp, and a battery linked together through a few pieces of short wire. So when you turn the switch on, electricity flows around the circuit. But if there's a break anywhere in the circuit, the electricity cannot flow, right? For example, if your light bulb goes, like if one of the wires isn't connected, your lamp's not going to light up. So think about this. If the switch is turned off, no electricity will flow. And then some materials are like metals or electrical conductors because they allow electrons or that current to move through them easily. And the other materials like rubber, they don't allow electrons to flow, and these materials are called electrical insulators. So electricity and magnetism are closely related. We know magnets are an object made of certain materials, including iron, which create a magnetic field. And magnets also exhibit the property of magnetism in which they're able to attract or repel certain objects that can align themselves in an external magnetic field as well. So while it's easy to think about that all metals are magnetic, iron is the only common metal that is magnetic, okay? But iron is very common. It's inexpensive and useful, so it's found almost everywhere. So the areas on the magnet where the force is the strongest is called the poles. Magnets have a south pole and a north pole. And the north pole of one magnet attracts the south pole of another. So opposites attract with magnets. An electromagnet is a magnet that can be switched on and off with electricity. So think about a junkyard, right? Junkyards use giant steel electric magnets to help move stuff around. And when the current flows through an electromagnet, it works like a magnet and generates a magnetic attractive force that can pick up large pieces of steel. But when that current stops, it goes back to just being an ordinary unmagnetic piece of steel, and you drop the junk where you want it, right? A really good thing to do is during this unit is to allow your students to make an a mini electromagnet. So magnets don't need air to work, and they can still pull on magnetic material in a solid or a liquid. And that's a misconception that young students have. And what's also really cool that you can share with your students is the Earth's core has iron, so it has its own magnetic field. And we know that from our compasses, right? Our compasses always point to magnetic north here on Earth because our core has iron in it. So let's look at some activities. Before that, let's talk about phenomenon. So for each of these units, you're going to use a phenomenon, a naturally occurring thing in the world that strikes your students' fancy. It's going to activate their science thinking. It's going to get them asking questions and thinking about what you're showing them. But with that phenomenon, it can be a video clip, it can be a photograph, it can be a demonstration, it could be a nature walk around the school. But after you show that phenomenon, students are going to write questions and post them on what you're going to create called a driving question board. It's basically just an anchor chart for all of their questions, right? So if you look at the graphic on the right, the students are going to generate their questions, and then the students are going to rotate through stations during their work session using those science and engineering practices from our standards. Remember, plan and carry out an investigation, construct an argument based on evidence. They're going to do that during the work session in order to communicate and connect to the science content and those cross-cutting concepts. Therefore, they're going to be able to communicate their findings with you and answer those questions that they had at the beginning of the unit. So you're coming back to that phenomenon every single day before your students start working on their science stations. And you're referring back to it every day and looking to see if you can answer any of those questions. So for physical and chemical changes, an anchoring phenomenon that you could use is elephant toothpaste. So I'm going to show you this YouTube video clip so you can see exactly what I'm talking about. It's only 30 seconds long. I'm sorry, there is a political. We're just going to skip that. And it is phenomenal. So I'm going to fast forward this. He's putting all of this in. So I'm fast forwarding so we can see exactly what happens. Oh. Okay, I'm sure you can find a less, a short version of that if you want, but that's a really good video clip to get our students thinking. So you show the video clip and then you have students write questions on sticky notes. Your face-to-face students can write it on their own sticky notes and post it. Your remote learning students, they can do it on a digital whiteboard. You can use Whiteboard-Fi. I've even had some teachers pull up a Word document on OneNote, and remote learners can type in their questions there. And you can also scaffold them with some guiding questions like, how does the liquid turn into the foam? Why does it continue to expand? What causes the liquid to change? To get them thinking about what they're about to do, because you're about to engage them in some really hands-on learning, right? So an example to hit up element A and B, plant investigations, physical or chemical change has taken place, is an activity from one of our Ames science books called Change Matters. So the main thing is that the key question for this activity that you will pose to students is, how do you know whether the changes you observe are physical or chemical changes, right? So they're going to identify physical and chemical changes, they're going to classify the changes in matter, and they're going to collect, graph, and analyze data. So you have different stations. So I have 4 of the stations right here for you. You'll need to put these materials at the station. For example, station 1. All they have to do is observe an ice cube in a plastic cup for a few minutes, right? And then they have their lab sheet where they record their observations. They're saying whether it's physical or chemical, they're checking whether it's physical, chemical, or both, and why, right? You know, station 2, use tongs to dip a small piece of still wool into a cup of vinegar, place the still wool on a paper towel, observe. So really easy, small things, not a lot of materials. Your friends at home, your remote learners at home, you could do this live as a demonstration. You could do this whole group if you wanted to. Each day, pick a different procedure to do. Have them pull out their observation form. Once you've done all of the stations, students will then do the Venn diagram where they indicate, the proper placement of each change. Okay. So this is a great way to get them thinking about physical and chemical changes and get them engaged in hands-on science as well. All right, another one is called mixed reactions, right? And this one is going to hit up that third element on chemical changes. These are all chemical changes and whether or not we can tell if a chemical change has taken place. So they're going to have different stations again. They're going to conduct tests to check for a chemical reaction. They're going to classify the tests based on whether it has taken place and identify the production of a gas and a temperature change as evidence, right? So this evidence of a chemical reaction is what I would make as my anchor chart for this activity. To me, it definitely shows definitely shows the different ways that we have evidence of chemical reaction. And here it does, you are going to need a few more procedures, materials for these stations, but you can have all those laid out. Like I said, you could do it whole group if you wanted to. So for example, station number 2, hydrogen peroxide and sugar. Pour 40 milliliters of hydrogen peroxide in your cup. Find and record the initial temperature. So you are going to need some digital thermometers or things like that. You're going to add 1 spoonful of sugar to the cup, stir, find and record the temperature after adding the sugar. Observe for 3 minutes and record any observations. Find and record the ending temperature, clean your area. It gives you the data table, right? The one above it where it has all the stations upside down and forward. That's what you're going to take your data while you're doing the stations. And then afterwards, you're going to graph the temperature change, if there was one, for each reaction, and making sure you write the beginning temperature of each station, and then label the graph along the left side. So it's really hitting up that element C really well. And you're getting that data piece in there. You have that math integration, and your kids are analyzing. So that's huge for 5th grade. All right, so for the states of matter, the one about water and the changes in the states of matter, I have an amazing STEAM activity for you to do. It's called using movement to explore states of matter. So students are taught through a video clip about different types of locomotor and non-locomotor movement, and they learn dance moves, right? I mean, I'm not the best dancer, but I will get up in front of my kids and make a fool of myself if it's going to keep them engaged. So what happens once they learn all the dance vocabulary is you give them the opportunity to come up with what the particles because really in the states of matter, in this element B, we're looking at how the particles move during the different states of water. So you can give them a state of water or maybe even a picture of water, and they would have to come up with a movement to demonstrate that state. So if we're doing a frozen glass, right, or your state of matter is frozen, you could be non-locomotor and standing straight and tall, right? And then you can also have them extend this to being one state of water, and then you have to create an 8-count dance count to move from frozen to solid or solid to gas or something like that. And let me tell you, I've done this with 5th graders for many, many years, and they absolutely love that activity. And then last but not least, a really fun one to do if you're wanting to do some sort of summative assessment is an AIMS activity called product testing, and they're making Glubber. So it's what is the best formula to use to make Glubber. So definitely math integration in here. They're actually making Glubber, but they're utilizing and identifying percentages, comparing and contrasting properties, and then recommending a product formula based on their data. So it's going to give you 3 different recipes, and you got to figure out based on after they're making them if which one of them is the best recipe for the Glubber product. All right, electricity and magnetism. I promise we're almost done. And remember, all of these activities are going to be provided to you via a link on Teams afterward. But my one of my favorite electricity and magnetism phenomenon is that heavy electromagnet video clip. So here's an anchoring phenomenon that you can use. Short, you don't have to show the whole thing. This is a big, huge electromagnet. All right, so you see that quick little short video clip. You show that to your students and get them thinking about, you know, what is happening. You can scaffold with these guiding questions. Since iron and metal are attracted to magnets, how does the crane operator get the metal to repel off of the magnet? Can you turn a magnet off and on? So, you know, getting their thinking, getting those questions down on that guiding question board. You're going to come back to that electromagnet every day. How I love to do these, the hands-on science with this unit is I start with this activity called All Charged Up. All you need is a wooden meter stick and 2 balloons, and it gives you the procedure right there. This is a great demonstration that you can use. So you balance that meter stick on the edge of the table so it's barely in place, and you ask 2 students to inflate a balloon. Those students rub the balloon on their hair, and then have one student stand on one side of the meter and the other student on the other side, and you challenge the students to try to pull the stick to his or her side. And it actually does move, and you kind of discuss with them why this happens. Don't give them the answer. Say, we'll come back to this at the end of the unit and talk about it. It's another great phenomenon. Static electricity and statically charged objects are going to be investigated in this activity called different strokes. So it's basically you're going to need balloons, and you're going to experiment with static electricity and discover some of its properties. So here it's you'll need some of these things if you don't have it, like a pencil, some thread. You got pencil shavings you might not have, and then same thing, you do it with 1 balloon, and then you try it with 2 balloons, about 3 to 5 centimeters apart, with the material in between to see what it's attracted to. So, or what its static clings to. So manipulating static electricity. And then there's a really good conductor and insulator activity where students are investigating, which is one of the standard elements. It's investigating what materials conduct electricity. So they're going to test a variety of materials to determine if they're conductors and insulators. So it gives them background knowledge on that, but it also tells them you're going to need a D-cell battery. You're going to need some copper wire, You're going to wrap that around the metal side of the, and you're going to need a small light bulb. You can purchase those at any dollar stores and things like that, or you can buy some LEDs, but it shows you kind of here on the page how it needs to look. So you tape the wire, the bottom of the D cell, and then that wraps around the bottom of the light bulb. Then you're going to tape it securely in place, right? All right, so you're going to test each item. You're going to put the light bulb, you're going to put the bottom of the light bulb on that object to see if it lights up, right? And if it does, it's a conductor, and if it does not, it's an insulator. And then they can do the conductor and insulator Venn diagram with that. I have a packet about circuits, making simple circuits with diagrams, and walking through students how to make simple circuits. But one of my most favorite things to do is paper circuits, right? With LEDs, copper tape, and coin batteries. But the packet that I'm sharing with you has these templates, as you can see on the paper, for a simple circuit that walks them through where each component needs to go. And then you can make that activity your own. You can make greeting cards with it. You can seam it up and add some art standards in there. All this packet for the paper circuits has many different templates. It has series and parallel circuits as well. And they can do investigations to see how many or what different materials can help them complete their circuit. So lots of hands-on activities to do for these. I'm going to stop sharing my screen really quickly with you so I can share. So I can share with you what the paper circuit looks like. So I said I had lots of templates for that. So this is a double template that you can do. I just have a name tag for mine. I have, it has series. These are the papers that it comes with lab sheets that you can see here. It's called Bright, Brighter, Brightest. It says, I predict that the brightness of the LEDs is going to be whatever. So they fill in the blank there. And then after connecting the different types of paper circuits, observe the brightness of the LEDs, rate the brightness, and write the numbers in the table from 1 to 5. But it gives you all of the templates. So you have simple 1, simple, series 1, series 2, parallel 1, parallel 2. And for each circuit, it's telling you the number of LEDs. It shows you on the template. So for example, let me show you so you know what I'm talking about. So you're like, what? Okay, so here is a series paper circuit. The 3 things right here are where the LEDs go.
I'm sorry, I can't do that for you.
My Apple Watch. Okay, so you have your 3 LEDs here, and you're going to predict the brightness, and it does that for 2 different series ones and 2 different parallel ones with different numbers of LEDs. So that's a really fun activity to do for designing and completing circuits. So that's it for me. Like I said, all of these resources and materials and the PowerPoint are going to be uploaded to the Microsoft Teams whenever I'm done with this recording. Other than that, that is quarter 3 for you. I hope you have that. If you have any questions, please reach out to me and let me know. Other than that, that's it for me. Thank you.